This is lecture one for IE 4355 Facilities Planning. And the title for this lecture is Product Process and Schedule Design. So the course objectives for facilities planning, IE 4355, are the following. First, we want to develop an understanding of the principles of facilities, location, layout, and material handling systems, and to practice designing facilities. Second is to learn formulations, models, and analytical procedures for the study of facilities layout planning. Third, learn fundamental principles of material handling. And four, be able to design layouts incorporating product process and personal requirements. So this lecture is going to touch on several of these objectives, particularly on that last one, objective number 4. So the agenda for this lecture includes the following 4 topics: product design, process design, schedule design, and facilities design. In terms of the learning objectives for this particular lecture, we're going to learn the product process and schedule design functions as they relate to facilities planning. And also we want to understand the interactions between facilities planning and the product process and schedule design. So as illustrated in this figure, facilities design is in the middle of these 3. Product process and schedule design. So they are all of them are part of or are really important in terms of making decisions in how to design our facilities. We have to take these 3 areas into consideration. So let's start with product design. The product design involves both deciding which products are to be produced and the detailed design of individual products. So decisions regarding the products to be produced are generally made by upper-level management, but the design of a product is influenced by the aesthetics, the function, materials, and the manufacturing considerations. So marketing, purchasing, industrial engineering, manufacturing engineering, product engineering, and quality control, among other factors, will influence the design of the product. So in this figure here at the top right of this slide, you'll see a design for a cell phone. So all this aesthetics, function, materials, and manufacturing considerations are all important in this final design, taking into account how it's going to be produced, what type of materials is going to be used, what are the dimensions, and so on. So in terms of product design, pictorial representations, as the one that I illustrated or presented in the previous slide, and prototypes of the products are important inputs for the facilities planner. And in this figure number 2, we're showing what is exploded assembly drawing. So these are all the components and how are they assembled in order to get the final product. So as you can see here, we have 11 parts, just an assembly of 11 parts, and then put it together, we have a final product, or could be just a component of a major product. So all these things are very important. So we need to know what materials are needed, the order in which there are the assembly is performed, in order to locate the stations, locate the materials, and locate the people that are going to be performing these activities. Photographs and drawings allow the planner to visualize how the product is assembled. So if we have information, not only the drawings, but if we can present how those parts are actually, how they look in real life, that also helps. Provides additional information. I mean, we can see the materials, we can see how they look in terms of dimensions in real life, and those things are very important in terms of visualizing how the product is assembled. Detailed component part drawings are needed for each component part. The drawing should provide part specifications and dimensions in sufficient detail to allow part fabrication. So if you're going to be fabricating these parts in the facility, then you need to know the dimensions really well. That's the purpose of this type of drawing that is illustrated in Figure 4. And the combination of the exploded assembly drawings and the component part drawings fully documents the design of the product. The reason I'm showing drawings in these cases and knowing the dimensions is because as a facility planner, you have decision whether you want to manufacture all your parts in the facility or if you want to buy them from a supplier. So both decisions have their advantages and disadvantages. But if you decide to produce in-house, then you need to have this level of detail in order to make that happen. So the drawings can be prepared and analyzed with computer-aided design or CAD systems. Concurrent engineering can be used to improve the relationship between the function of a component or product and its cost. So cost is very important. And we're going to touch on this later on. Those decisions that I mentioned on the previous slide, whether you're going to build in-house or you're going to buy from a supplier, those decisions are mostly based on what's more efficient in terms of cost. So concurrent engineering can help you improve the relationship between the function of the component in the product and its cost. Functions are integrated to reduce the elapsed time required to bring a new product to market. So concurrent engineering provides simultaneous considerations in the design phase of life cycle factors, such as product design, materials, manufacturing processes, testability, serviceability, quality, and reliability. So using concurrent engineering, instead of waiting for one step to be completed to move to the next phase, there are multiple phases of the development of these products that are happening simultaneously. That's the idea of concurrent engineering. So you are performing these activities in parallel so you can move faster in terms of bringing that product to the market. So let's talk about process design. Process design is determining how the product is to be produced. So as I mentioned earlier, you have to make a decision whether a part will be purchased or produced in-house. For parts that are going to be produced, the process designer must determine how the part will be produced, which equipment will be used, and how long it will take to perform the operation. All this very important. So how the part will be produced. So what type of process you're going to be using to produce that part. Which equipment. Equipment is important in terms of space. So if you're going to be using equipment that is going to require a lot of space, then you have to take that into account when designing the facility. If it's a product, if it is a process or equipment that is going to be producing a lot of noise, you have to take that into account in terms of where you're going to locate that equipment, that department in the facility, so it doesn't interrupt the operations of other areas. And how long it will take to perform the operation. That's very important too in terms of scheduling. That tells you, I mean, you can use that information to plan in terms of how many parts you can produce, for example, in a week, and so on. So these three are very relevant. The final process design is dependent on both the product and the schedule designs. So process design, identifying required processes. So as I mentioned earlier, you had the option as a manager, facilities planner, identify whether you want to buy or you want to make in-house. And those decisions require input from finance, industrial engineering, marketing, process engineering, purchasing, human resources, among others. So finance, they can tell you what's more efficient in terms of cost, industrial engineering in terms of scheduling, in terms of what's more efficient, in terms of how reliable are the suppliers, in terms of producing quality components and so on, marketing, process engineering, purchasing, and so on. Human resources, very important. You have the staff available and the expertise to produce that type of product. So here we have a flow chart on the right side of this slide that can help you in terms of making decisions of whether or not you want to buy or make in-house a particular part or product. So we start from the top to the bottom. And as you can see at the bottom, the last arrow is the one that says, okay, if you answer yes to all these 4 diamonds, then you can make in-house. That's your best option. But if you answer no to one of these questions at any time before that, then it's better for you to buy, unless the item cannot be purchased, which is what's happening at the top. So we have 4 questions. Is that item available? Will our union allow us to purchase the item? Is the quality satisfactory? Are the available sources reliable? If you answer no, then it's better for you to make. If you answer yes, then you can move to the next set of questions. Can we make the item? Is the manufacturing of the item consistent with our firm's objectives? No, then we buy. Do we possess the technical expertise? The answer no, then we buy. Is the labor or manufacturing capacity available? The answer no, we buy. Is the manufacturing of this item required to utilize existing labor and production capacities? The answer is no, then we can buy. But if the answer is yes, then we have to move to the next step. Is it cheaper for us to make than to buy? The answer is yes, then we move to the next step. The answer is no, then we should buy. And then finally, we have the last step. Is the capital available allowing us to make? The answer is no, we buy. The answer is yes, we make. For example, things to consider in this final steps is what are the other opportunities for the utilization of our capital? So is there any other investment that we can pursue with this money that will give us better income in the future, for example? What are the future investment implications of this item is manufactured? Can we, I mean, if we start manufacturing this item, can we sell this item to other suppliers or to other manufacturers, and so on? So moving forward, the input to the facilities planning is a listing, and we're still talking about product design, identifying the required processes. The input to the facilities planner is a listing of the items to be made and the items to be purchased. Okay, so I'm designing the facility. I need to know, okay, what are the things that we are going to be making in-house? What are the things that are going to be purchased? Even if I'm not going to be making them in-house, I need to make sure that if they're coming from somewhere else, I'm providing space for receiving those items and providing space for storing those items. An easy way for accessing those items when they're in-house and so on. So those, I mean, even if we are not producing them in-house, we still need to get that information in order for planning. The listing often takes the form of a part list or what we call a bill of materials. So here in figure 6, we have a part list for an air flow regulator. So as you can see, we have a list of parts. That's first column, part number. So each part we have a number, we have a name. If we have a drawing, then we will have the drawing number and how many are needed per assemble. The type of material, the size, and whether we are buying or making those in-house. The bill of material is often referred to as a structured part list. Contain the same information as part list plus information on the structure of the product. So the bill of material is similar to what we saw on this part list. We have some additional information, which is the structure of the product. And that's what's illustrated here at the level. So level 0 means that that's the final assembly. And then as you move down in terms of the number, so level 4, for instance, these are smaller components, and you put them together and you move to level 3, put them together, you move to level 2, put them together, you move to level 1 until you get to the final product. Okay, so that's the major difference. We can use this information to depict the assemble of the product, which is what we are trying to illustrate here. So typically the product structure is a hierarchy referring to the level of product assemble. So level 0 is usually indicates the final product. Level 1 applies to the sub-assemblies. So level 0, we have this at the top, it's level 0. And then, as I mentioned, level 4 are those parts that are put together. For example, here we have all these parts, right? You have all these parts, and when you put them together, you create this plunger. And then when you put them together with the body, you have the body assembled, which is level 2. So level 1 applies to sub-assemblies and components that fit directly into the final product. Level 2 refers to the sub-assemblies and components that fit directly into the first level, and so on. Once a determination has been made concerning the products to be made in-house, decisions are needed as how the products will be made. So process selection procedure involves the following steps. Step 1, we have to define the elemental operations. Step 2 is to identify alternative processes for each operation. So we have the options, then we analyze the alternative processes. We decide which one is better, and we standardize the process. We evaluate alternatives processes, and then select the processes, which is the final step. The facilities planner will not perform process selection. Understanding of the overall procedure provides the foundation for the facilities plan. So step one of the procedure involves the determination of the operation required to produce each component. In order to make this determination, alternative forms of raw materials and types of elemental operations must be considered. Step two involves the identification of various equipment types capable of performing elemental operations. So whether it's manual, mechanized, and automated alternatives, all of them should be considered. Step three includes the determination of the unit production times and the equipment utilizations for various operations and alternative equipment types. The utilizations are inputs into step four of the procedure. Step five involves an economic evaluation of alternative equipment types and the results of the economic evaluation as the basis for step six. So the output from the process selection procedures are the processes, equipment, and raw materials required for the in-house production of products. The output is generally given in the form of a route sheet, which is what is illustrated in table 1. So in terms of data, which is the column to the left, we have information about the component name and number, the operation description and number, the equipment requirements, the unit times, and the raw materials requirements. Unit time is how long it's going to take for you to produce this, right? In terms of the component name, so here we have an example, it's a plunger housing, and we have the number 3254. The operation description and number, these are the operations that are needed. So we have to shape and then drill and then cut. And the equipment requirements, automatic screw machine and appropriate tooling, setup time, and then 5 hours operation time. It's gonna take about 0.0057 hours per component. And in terms of the materials requirements, how much aluminum per bar per 80 components in this case. So all these things are very important. You have to plan for example, the equipment, you have to plan for the tooling, you have to plan for the scheduling, you have to plan for the location and the availability of the materials in order to produce this product. So here's the route sheet for one component of the airflow regulator. So this part name is the plunger housing for producing an airflow regulator. And here we have the operation number, the operation description, the machine type that is used for each one of the operations, tooling, the description of the tooling, setup time, operation time, and the materials. Okay, so in this case, we have the material has to be available for this per operation, and after that's completed, then that's going to move through the next operations, but you don't need any additional material for that. It's just refining that first operation until it is done. An assembly chart provides the method of assembling the product. The easiest method of constructing an assembly chart is to begin with the completed product and then trace the product disassembly back to its basic components. So here's the assembly chart for an airflow regulator. These circles are representing the assemblies. So A is for assemble, and then subassemble, SA, and then these are circles. Then we have square. This is representing an inspection. What else? So as this mentioned it, so the easiest way for you to build this type of a chart is to go backwards. Like you start with the final product and then you start disassemble the product until you see how it's connected. So for example, if we start here, that's the final assemble, which comes before this assemble is inspected. And this assembly right here requires the body, as we saw on the route sheet, and this sub-assembly of these components. These two come together into assemble one. Assemble two connects A1 and A2, or A1 to this lock nut, and then A3 connects this assemble to the pipe plug. Everything is inspected. Then you take the packaging materials and you put them into the assemble that you're performing in-house, so you can complete the airflow regulator. An assembly chart does not provide an overall understanding of the flow within the facility. We can obtain that type of information by superimposing the route sheet and on the assembly chart, a chart results that give us an overview of the flow, and that's called the operation process chart. So here's the operations process chart for the airflow regulator. So we are, again, combining the information from the route sheet and the assembly chart into a chart or a diagram. So what's happening here, you have the information in terms of the assembly and the of each component, but you also have information about the part number, and you also have information about the type of process that is needed for each part. So for example, here we have 0101. This is a part that needs to be cut to length. This is another part that needs to be grind to length. And then when you perform all those steps, and you have those parts ready, then you can assemble them into a component, which is going to be combined to other ones, as illustrated in the chart. To construct an operation process chart, we begin at the upper right side of the chart with the components included in the first assembly operation. If the components are purchased, they should be shown as fitting horizontally into the appropriate assembly operation. If the components are manufactured, they should be shown as fitting vertically into the appropriate assembly operation. The operation process chart may be completed by continuing in this manner through all the required steps until the product is ready for release to the warehouse. Second viewpoint based on the graph and network theory is to interpret the chart as network representations. The precedence diagram is a directed network and is often used in project planning. So the precedence diagram shows part numbers on the arcs and denotes operation and inspections by circles and squares, respectively. And this is an example of a precedence diagram for an airflow regulator. For the purpose of this class, we are not going to be using this type of diagram, the precedence diagram, but we have to know how to build and understand how an operation process chart is constructed and what it means, and how are they different to a route chart and to an assembly diagram. We also need to understand how to construct an assembly chart and what is this representing. So an assembly chart is important, it's required for the class. but the precedence diagram we are not going to be asking you to draw a precedence diagram in this class. So let's talk about schedule design. Schedule designs decisions provide answers to questions involving how much to produce and when to produce. Production quantity decisions are referred to as lot size decisions. And determining when to produce is referred as production scheduling. In addition to how much and when to produce, it is important to know how long production will continue. Such a determination is obtained from market forecasts. Specification of the process requirement typically occurs in 3 phases. The first phase determines the quantity of components that must be produced, and that includes allowances for defective items. The second phase determines the machine requirements for each operation, and the third phase combines the operation requirements to attain overall machine requirements. So let's start by calculating or trying to calculate calculation of production requirements. The required inputs to manufacturing and assembly operations can be determined as follows. So we're going to use DK to represent the percentage of defective items produced on the kth operation. OK is the desired output without the defects. This is how many we need to produce, let's say for our customer. And IK is the production input. So on the average, that output or the desired output without defects is going to be equal to our input minus those defective units. That is going to be computed as the percentage of defectives times the input. So the output or the desired output is going to be equal to the input times 1 minus the percentage of defective parts. We can solve for IK. So that input is going to be equal to the output divided by 1 minus the defective rate. So for products with n sequential operations, the expected number of units to start into production at the first operation is shown in the relationship below. So if we know what the output is, the desired output, this is how many we need to produce, or this is how many parts we need to move forward in the production or to send to our customers. In order for us to get, if we know that in our process we have some defective items or we expect some defective items, then we have to take those into account. So we can compute how many units we need to start with in order to get that output. Like if we need 90, but we know that 10% of our production is defective, then we need to start with 100 because we know 10 of them are going to be defective. So we get that final output, final desired output of 90. So that's the type of planning that we are doing with this process. We know the output, we need the output requirement. So we need to know, the question is, how many units we need to start with in order to get that output. So that's where this is an example. Here we want to calculate production requirements for a serial process with 3 operations. We have a product has a market estimate of 97,000 components and requires 3 processing steps: turning, milling, and drilling. And each one of these processing steps have a defective estimate. So for the first one is 0.04, for the second one is 0.01, for the third one is 0.03. The market estimate is the output required for step 3. Therefore, for each operation, turning, milling, and drilling, we have the production quantity schedule. So this is how many we are going to need if we need to have this as an output. So if we need to produce this many units, we need to start with this many parts. The question is, how do you get this? How do you get these numbers? Okay, you know you have this information. You have the defective rates that are listed here. So the question is, how do you get these values? So that's what I'm going to illustrate now. So as the problem describes, we have three operations, 1, 2, and 3. And we know that our desired output is 97,000. That's our desired output. And we know that this is a serial process. So we need to know how many units we need at the beginning so we can obtain this 97,000. But we also know that in each process, we're going to have a certain number of parts that are going to be defective, right? So this is D1, D2, and D3. Okay. So we need to compute what will be the input for 3, what will be the input for 2 in order to get to this number. And that's how we're gonna work this problem. We're gonna go backward. We're gonna start with the 97,000 and we're gonna compute based on the percentage of defectives that are expected in this third station. We can compute what is the input required for getting that 97,000. And then we can use input 3 to compute the input of number 2. And then we can use the input of number 2 to compute the input of number 1. So let's start with I3. We want to know what I3 is. As I discussed earlier, that's going to be equal to the output divided by 1 minus the defective rate. For D3, this is 0.03. So this is 0.03. And that number is 100,000, which is this number right here. So that input 3 is going to be the output of 2, right? So now I3 becomes output for 2. So output of 2 equals input of 3. So if I want to compute input of 2, my output is 100,000. And I'm going to divide that 1 minus the defective rate for 2 is 0.01. So this is 0.01. So 1 minus 0.01. And this is equal to 101,010, which is this number here. So in the same fashion, I2, my input 2, so the output of 1 is going to be equal to the input of 2. So I can compute I1 now. This is 101,010 divided by 1 minus the defective rate of 1. This is 0.04. So it's 1 minus 0.04. So the required input for this process is equal to 105,290. And that's the solution. So for me to be able, for this particular process, to get the 97,000 units that I need for moving to the next process or to supply to my customers, if I need 97,000 units, knowing that I have this different levels of defective rates through the operation, then I need to start with 105,219 units in order to get this 97,000.